Welcome everyone to our fourth and final lecture. So in the previous video, I talked about first the importance of dating. Why is it so important that we know how old the fossil is? And then I went over relative dating. That is the methods that tell us whether a site is older than another one, but not by how much. In this lecture, we'll go over absolute dating, also known as numerical dating. And so with this method, we can actually put a number on the age of a fossil and actually say how much older a certain fossil or site is than another. Okay, so absolute dating methods. And yes, for example, we can make statements like, this is 2 million years older than that. So in order to put a number on the age of a fossil, we need some type of clock, right? And the requirements for a numeric clock in this case are, number one, we need something that happens at a constant rate. Number two, we need some way of knowing how many times that thing has happened. So for example, we have a clock, right? Minutes go by at a constant rate, for example, 60 seconds. So check mark, so we've checked off and fulfilled requirement number one. Let's say 40 minutes have happened and elapsed, right? That checks off our requirement number two, knowing how many times that thing has happened. So we know that minutes happen at a constant rate, 40 of these minutes have happened, and so that provides a numerical estimate of time, right? And so this is the general principle by which these numerical and absolute dating methods work. So our first requirement for a numeric clock is something that happens at a constant rate. Well, luckily in nature, radioactive isotopes decay at a constant rate. And isotopes are just variants of the same element. So for example, you have element carbon. There are different variants, which are different isotopes. You have carbon-12, which is a normal one. You have carbon-14, which is radioactive. So in this case, that is one of the radioactive isotopes that decay at a constant rate. Not really important for you to know exactly what an isotope is. So we have a radioactive parent isotope, right? These radioactive isotopes are very unstable. And so what happens is over time, they decay into a stable daughter isotope. We measure this in half-lives, which is the amount of time it takes for half of the parent to decay into the daughter isotope. So here's a picture showing that, right? So let's say here, let me get my pointer. Okay, we have the formation of, let's say, a rock, and the isotopes within the rock have 100% parent isotope, radioactive, no daughter isotope. After one half-life, half of the parent isotope has decayed into the daughter isotope. After the second half-life, half of that half, that is 1/4 of the parent isotope remains, and you see the amount of daughter isotope has increased, and so on and so forth, right? We have 1/8 of the parent isotope remaining, and we have the daughter isotope. So these radioactive parent isotopes decay at this constant rate, measured in half-lives, right? And we see the change in the ratio of parent to daughter isotope. So that is the first requirement, right? Something that happens at a constant rate. Radioactive isotopes decay at a constant rate into the daughter isotope. So we need some way to be able to measure the amount of parent and daughter isotope, right? And that basically is requirement number two, knowing how many times that thing has happened. So let's go through an absolute dating method together so this all comes together and makes sense. So the method I will be going over is known as potassium-argon dating. This is a very popular one, especially in Eastern Africa, where you have a lot of ancient human fossils. That's because Eastern Africa is a very volcanically active region. So we get a lot of things like ashes, right, when the volcano erupts, and ashes are what you date using this method. So we're dating volcanic strata. Excuse me. And it's important to illustrate and emphasize here that, so because we're dating volcanic strata, we're actually not dating the fossil itself, right? What we're dating are layers bracketing the fossil. So here we have a fossil. Underneath is a volcanic deposit that we can date 3.8 million years ago. And because of the law of superposition, we know this fossil is younger than 3.8 million years ago. And we have a volcanic strata overlying the fossil, which is dated 3.2 million years ago. And because of the law of superposition, we know this fossil is older than 3.2 million years ago. So because this fossil is bracketed by these two tufts, or sorry, volcanic ashes, we know it's between 3.8 and 3.2 million years ago. Okay, so how potassium argon dating works is, well, first the volcano erupts and spews all of this ash, right? And initially, the mineral crystals in the ash have radioactive potassium-40, but none of the daughter product argon-40. And that's because of the immense heat of the volcanic eruption actually drives off any argon in the crystal. Okay, and over time, the radioactive unstable potassium-40 decays to the stable daughter isotope argon-40 with a half-life of 1.25 billion years. Long, long half-life. And we can use a fancy machine called a mass spectrometer to measure how much potassium-40 there is and how much argon-40 there is, right? This is the second requirement of the numeric clock. And then once we measure that, we can actually estimate the age. Right, so again, that fulfills the requirement number 2, knowing how many times that thing has happened, how many times the radioactive parent isotope has decayed into the daughter isotope, right? If we can measure the amount of parent isotope relative to the daughter isotope, we know how many times that decay has occurred. Okay, so this is a summary sheet of potassium argon dating. It's the parent radioactive isotope, the stable daughter isotope, right? Huge, very long half-life. And because the half-life is so long, it can actually date fossils or volcanic rocks, I should say, from 100,000 years all the way to Earth's origins about 4.5 billion years ago. Again, it's used to date volcanic rocks. And here is just a graphical representation of the parent isotope decaying over time by half, right? And you can see the number of half-lives that have elapsed, the number of associated years with that, in this case in billions of years. And so if we can measure this using our mass spectrometer, we can infer this, the numeric age. So virtually all absolute dating methods follow this principle. There is something that happens at a constant rate. It's always usually a radioactive parent isotope decaying into a stable daughter isotope. And we use fancy machines to measure how much parent isotope there is versus how much daughter isotope there is. And with those two lines of information combined, we can actually put a numeric age on whatever it is we're dating. Okay, so here's a really famous one. Perhaps you've heard of it. This is radiocarbon dating. So it pretty much follows the same exact principle that we covered with potassium argon dating. So in this case, carbon-14, which is the radioactive isotope, it's produced in the atmosphere. And what happens is radiocarbon or carbon-14 is oxidized and forms carbon dioxide. And so that carbon dioxide with carbon-14 is taken up into the plants through photosynthesis, which is then eaten by mammals, in this case a mammoth. And when either the mammoth or the plants die, they stop incorporating carbon-14 into their tissues. And so what happens is that carbon-14 starts decaying into its daughter product, nitrogen-14. And this happens at a constant rate. And so if we can use something like a mass spectrometer to measure how much carbon-14 there is versus how much nitrogen-14 there is, and we know how long the half-life is, we can actually date and put a number on how old this mammoth fossil is. And here's that summary sheet for carbon-14. So you can see here the half-life is much less, and therefore the maximum dating range for carbon-14 radiocarbon dating is much, much less than potassium argon dating. And it's used to date organics, right? Bone, charcoal, anything that was once living, anything that during its life was incorporating carbon-14 into its tissues. So there are many absolute dating methods. I'm not going to go into these. They follow the same principle that we covered with radiocarbon, with potassium argon. But you can see there are many dating methods. And within paleoanthropology, the time window we're interested in is right here. And so we use all of these different methods to date whatever fossil we're interested in. Okay, so there's one more method I want to cover that's not quite absolute, not quite relative, and that's called paleomagnetism. So paleomagnetism involves reversals in the Earth's magnetic field. So if you took out a compass today, right, the needle will point towards the North Pole. But this was not always the case. At some points in the Earth's past, if you took out your compass, the needle will actually point in the exact opposite direction to the South Pole. So this always blew my mind, but over Earth's geological history, the Earth's magnetic field has flipped back and forth for reasons that are still not quite understood. Right? These are geomagnetic reversals. And here we have what are called crons. So these are long periods of the same polarity. For example, right here are the four most recent crons. So right now we're in the Bruns cron, right, which existed from 800,000 years to the present. So Ka stands for kilo annum, right? Kilo meaning 1,000. So that's the abbreviation for thousands of years. So from 800,000 years to the present, if you took out your compass, your needle would point to the north. But older than 800,000 years, all the way back to 2.6 million years, if you took out your compass, your needle would actually point to the south. And if you go back further, it's normal again. If you go back even further, it's reversed again, and it keeps flipping back and forth, as you can see, this black and white, black and white. And subcrons are just shorter reversals within these longer cron periods. So here are the crons I have listed here. And you can see these shorter reversals called subcrons, which all have names. And the way we're able to know when a rock forms, whether our compass was pointing north or south, that is whether the magnetic field was normal like today or reversed, is, well, what happens is that when there's a volcanic eruption and there's lava and it's still in a liquid form, all of the magnetic minerals within that liquid lava, they align with the direction of the magnetic field. And when the lava cools, those minerals are locked in place. So even if the magnetic field of the Earth flips, right, it will not affect the alignment of the magnetic minerals in the lava. That's right. So minerals will point to wherever magnetic quote unquote north was. And so when we find these rocks, we know whether the magnetic field, our compass, was pointing north or south, but we don't really know how old that rock is, right? So this is where we use other dating methods to tell you which specific cron or subcron you're in, right? So let's say we found a rock that had a normal magnetic polarity. So if we took out our compass, right, it would point north. And associated, we have mammals that are quite young. Let's say we know they're about 500,000 years old. So we know that rock was formed in the Bruns cron, and so that rock has a maximum age of about 800,000 years. So paleomagnetism helps us constrain the ages of these fossils and strata even more in combination with other numerical dating methods. Okay, this is same with biostratigraphy. So in the previous video, I explained and illustrated how biostratigraphy is used as a relative dating method. But if a species has been dated at a certain site using other numerical methods, absolute dating methods, then finding that same species at another site will give us an idea of age. So for example, again, we're going to be talking about pigs. Very useful for biostratigraphy in East Africa because of how that molar changes through time. And so given our study of the history of study of pigs and how long they span the fossil record, in combination with dating methods used to date that record, we know when these different species appear and disappear now. So if we're at a site and we find this species, Metridocaris andrewsi, we know that that site has to be between 2 million years, when Metridocaris andrewsi appears, and 500,000 years, when andrewsi goes extinct. Okay, so that is the section on absolute dating, aka numerical dating. And now I just want to finish up with a brief illustration of the geological time scale, right? So to give you an appreciation of deep time, how old is old, right? I've been throwing around millions of years, thousands of years, billions of years, but we humans are not good at interpreting large numbers. So I want to go through an analogy to really give you a sense of how old a lot of these things are. So here is our geological timescale. Earth formed 4.6 billions of years ago. So that's GA, giga annum, right? Giga stands for billion. So from 4.6 billion years ago to 542 million years ago, we call that the Precambrian, and that basically encompasses 90% of Earth's history. And after 542 million years ago, we have what's known as the Paleozoic. So the reason this boundary is so important is that this is when you get the appearance of complex life in the fossil record. If you ever want to see how weird some of these animals looked, just Google image search the Cambrian explosion. Some of these things are wild. So Paleozoic, right? This is the age range, 542 to 250 million years ago. This is the age of things like trilobites. And then you get this massive extinction event, the largest one in Earth's history, even bigger than the extinction of the dinosaurs. You get the Mesozoic after that. That's the age of the dinosaurs from 250 to 65 million years ago. And then you get that asteroid hitting Earth. You get the extinction of the dinosaurs, and then you have the age of the mammals known as the Cenozoic. And that is dated from 65 million years to the present. And you can see how the geological timescale is nested, almost very similar to Linnaean's nested hierarchy for taxonomy. And in this class, well, if I went over primate evolution, we would start here. But because I skipped that and we're moving right into ancient humans, we're going to start about here, right? So we're only covering this amount of time, which really is a blink in the eye. Blink of the eye compared to the rest of Earth's history. And to really illustrate that point, we're going to use an analogy. So let's take all of Earth's history and make it equivalent to one calendar year. So Earth is born on January 1st, right? And from then until April, there is no sign of life. In early May, simple life begins. Between summer and early fall, you have the appearance of single-celled organisms. And in early November, you have the appearance of multicellular life. Late November, you get the appearance of vertebrates. Last week in November, you get the first land plants and amphibians. And in early December, you get the first reptiles. So in the very last month of the year. December 10th, you have the domination of dinosaurs. And in December 15th, you get the first mammals, the Rockies form, and dinosaurs go extinct. So you get the appearance of mammals with only 15 days remaining in the year. Okay, at 5 p.m. on New Year's Eve, you get the first ancient humans, our ancestors, the first bipeds. At 11 p.m., 1 hour to go, you get the appearance of stone tools. With 15 minutes to go, our genus evolves and appears. And with 2 minutes remaining, you get complex civilization. So the whole point of this exercise is to show you just the depth of geological time, and really the part that we cover in this class really is like a blink of the eye, right? It starts 5 p.m. on New Year's Eve. Okay, so that ends our video 4. So in summary, what have we covered? In the first video, we defined what is a fossil, right? We went over body fossils, trace fossils. And in the second video, we talked about taxonomy. How are specifically body fossils? How are they preserved? How do they form? In the third video, we kind of pivoted and we talked about the importance of dating. Why is that so? Why is it important to know how old the fossil is? I gave you some reasons, and then we went over the first category of dating, that's relative dating, just saying that this is older than that. And in this video, the final video, we covered absolute dating, aka numerical dating, which is actually putting a number on how old these fossils are. And so instead of, or in addition is just saying that this is older than that, we can say this is 2 million years older than that.